Hi there. So you're making a game in Unity and you're getting stuck with the MonoBehaviour and game object approach. Maybe you're hitting some performance issues, it's lagging a bit every now and then, just enough to annoy you. You're finding frames don't render quickly enough in a consistent manner. Well, it turns out the underlying technology in DOTS, the data-oriented tech stack as they call it, are the job system, the Burst compiler, and Unity.Mathematics. And these are out of preview, right? They're production ready, they're stable. And you can get quite a good amount of performance out of them. Now, I've just spent the last 2 weeks or so trying to find out exactly how much performance I can get from these for my own project for BattleQuest. And I wanted to find out how easy they were to use, and what kind of complications there might be, especially given the documentation in Unity at the moment for these are either missing or super simple. So, how good is this for something more complicated than those simple examples? Okay, so this video is a little lengthy. It's at the moment looking around 26 minutes or something, 25 and a bit. It has taken about 2.5 weeks to produce various bits of research to create the material behind this. I've tested various parts of the job system and looked at the performance of different elements and use the Unity profiler to prove how many threads are being created or how the work's being scheduled across threads. It would be very rewarding if people could sort of support the work I'm doing. There's a GitHub project the link for that will be in the description below, and you can even install that as a Unity package, or rather you can install it as a package through the Unity package manager. So there's a fair bit of work that's gone into all this. Please hit that like button, please share it. Subscribe by all means, that'd be great. Okay, now moving on into the material. So basically what you're going to see is a description of the old MonoBehaviour way of doing things, and just as a comparison to set the scene. We're going to talk about the job system and what it introduces, what kind of new opportunity it creates within the Unity game engine for executing code, and how it breaks out of the old MonoBehaviour paradigm. So after that, we look at job types, we look at how you can chain jobs together and create a pipeline, how using the job system or building for the job system and using all the tools available gives you access to the vector processing instructions of most of the modern processors. And it's worth highlighting that the vector processing concepts actually come out of the old supercomputers like the Cray and so forth from back in the 70s or thereabouts. So that's what you're going to see in this video, and I'll put the time markers in the description below as well, so you can sort of skip ahead to the stuff you're particularly interested in. I hope you enjoy. Okay, so let's talk about the problem with monobehaviors. Right, so the problem with putting all your code in monobehaviors, just to cover this off, right, is that you're going to fall into the trap eventually of having a loop somewhere that has to perform logic across multiple objects or consider options or import or something that will just run a bit too long, maybe because there are too many objects, too many cases to consider, whatever, and as a result that's going to slow rendering that particular frame down, and that leads to that sort of spurt sort of lagginess in the game. And if it's not you that does that, it could be that because in C# you tend to allocate, if you're creating class instances, objects from classes, then you put pressure on the garbage collector, and the garbage collector eventually has to reclaim some of that memory. So it will kick in and it will mark a number of objects that are no longer in use, and then eventually it will collect them, sweep them up. So, if we have a look at this slide now, we can see just get an idea or an overview, tongue twister again, of the challenge with the game object approach, right? So we can see here that you've got the main thread, as Unity now tend to call it. It's classically been known as the game loop. We're scanning for input, dealing with physics, the game object update method or fixed update or on, the on collision entry, on collision exit, all that stuff gets called there. Then you get animation, some aspects of the garbage collector, rendering kicks in there, or at least it's triggered there. And so that's where these are the things we're competing with, right? These are all the events that need to happen within a frame render time that we're competing with. And if you open the if you open the profiler window, you can see this, right? So if you go to Window Analysis, hold on. Window Analysis it is. If you go to Window Analysis Profiler, you'll get the Profiler window, and in that you'll be able to see, up the top line, you'll see these key events that Unity is doing, or these key tasks that Unity is doing. And then in the underneath, if you click on the top, so you choose a certain frame to profile into or dig down into. And sometimes you have to turn on, up the top tabs of the profiler window, you have to turn on deep inspection or deep profiling. But then you can basically see your update methods being called and what functions inside that are being called and where's the time being spent. So you can actually see this for yourself. And I encourage you to explore that in your own projects. The other thing you can do is and this actually took me a while to find, but in the game window, in the Unity editor, you've got the scene window where you can lay out your objects, and then you have the game window where you can see what your game will look like. And in the game window, there's a new stats button. I won't say new, it's already been there for 2 years and I never noticed it, but the point is it's relatively new in Unity timeframe. So you can hit that and you'll get stats that highlight how many frames per second, how much time is being spent in the main thread versus other threads. So that's very useful. Okay. Now, if we go to the next step and think about what happens with the main thread versus using jobs, right? So this is where the C# job system gives us some new tricks. So there's a couple of things. There's obviously the jobs themselves, which can run in other threads. There's also this stronger distinction that Unity have created between, the C# managed .NET space and the native code parts of the player, because the Unity player has a fair bit of C++ code. And, we can see in this slide here that you're getting a few things. You've got the, let's take a step back. With .NET, right, that gives you guardrails to stop you from going outside array boundaries and protects you from memory leaks and things like this. But then you also get class-based instances being allocated on the heap, and it gives you the garbage collector, so that's avoiding memory leaks, right? So this is what managed .NET framework gives you. But when the job system, and the distinctions that Unity have created, we now have ways to break out of that a bit, right? That works within the Unity framework. So we bypass the garbage collector, or we can do, by allocating large blocks of NativeArray objects. And by doing that, we can essentially just reuse this memory. We allocate it up front, reuse that memory, and then that avoids putting pressure on the garbage collector, and it performs very well, right? Doing that performs very well. And you can hold this memory for the life of the game. So you allocate it up front, and you wait till the very end of the game with an on destroy, and you basically dispose of that memory at that point. Now, the other thing is you'll notice that there's a native array, that's one of the new types. The native array struct has entry points that basically control the native implementation. So all this code is actually implemented in C++, but you have these entry points in the C# space. And you also have this job queue and these worker threads that Unity creates for you. So by creating your jobs, now with jobs, the way it works is you have to write them as structs. So this is very clever, again, what Unity have done here by using structs in C#. These are value types. They are allocated on the stack. They don't go on the heap, so they avoid pressuring the garbage collector. So you can create a job. The job basically in your struct, you can put whatever data parameters you need for your task, and then you have an execute method, which is the job itself, which is the work to be done, and then you can just schedule that work. So again, this is in the main thread. You would, in maybe an update method, you would schedule the work to be done, and that's all you do, right? And so that work is then going to be done in another thread in parallel with the main thread. And that's how so now you use the main thread more to coordinate and orchestrate, and you push that work into the background threads in Unity. So this is the distinction that Unity has created, and this is a key thing to understand about how the job system works, and how this creates a new facility basically for spreading work out and doing this complex work in these background threads. And they can take as long as they take. That's the other nice thing. So they can, and you can find out through the job handle. We'll get into this a bit later, but you can find out if they're done, and then you can get the results back. So they can actually run over multiple frames.
So there are three general types of job, or you might say there are four if you want to make the distinction between the last two on the slide. But basically the iJob is something that will run on a single thread, and it runs to its complete, and that's it. And its interface is very simple. It's just an execute method with no parameters. All the parameters that are required by that particular task need to be instance variables for the struct. The iJob4 is kind of like a for loop or an iterating job, where the index into it sort of assumes you're going to be indexing into a native array. So you're given an index number into your execute method, and you basically can perform work according to that index. Now that can be scheduled just with the regular schedule method, and it can be scheduled with schedule parallel. And then you have the iJob parallel for, which basically looks the same in terms of the interface as the iJob4. It has the same. The execute method has the index parameter, and the kind of protocol for how you work with it. That index parameter must be, it's the only index you can use in the native arrays supplied with a job. So they're very similar in that regard, but the difference is if you do a schedule parallel on an iJob4, that seems to work exactly the same as an iJob parallel 4, just with a regular schedule method. So that's a curiosity of the way they've set this up. I guess if you go with an iJob4 type job, right, if you use that particular interface to define your job, then you have the freedom to make it parallel or not, and that's kind of a decision you can make. But I have tested through the profiler, and indeed these things work as they are documented to work, which means that if you do an iJob, that only runs on one worker thread. If you do an iJob4, that works on, it depends on how you schedule it, but it could work on one thread with the schedule, or multiple threads with the schedule parallel. And the iJob parallel 4 only has one type of schedule method, and that is schedule, but it will be parallel. So that is multiple worker threads will be dispatched. So that's the high level of your job types. The iJob parallel for transform is actually a very cool thing, and it's the same kind of idea as the iJob parallel for, in terms of, yes, things run in parallel, but it's, you have a transform access array that you pass in to the structure, or it should be one of the members of the structure. And so you've got an array of transforms, and so that's how you can, within a job, how you can actually move objects around in the scene or set new positions and rotations for objects, like thousands of objects in your scene. Job chaining. Right, so as you can see in the slide, it explains that what we could do is use a native array, and in this native array we could pass data from one job to the other, which would make them dependencies or dependents. So as you can see in the slide, we have a var handle 1 for a job.schedule. The .schedule didn't quite fit, so it's carried over to the next line. But the idea here is that's scheduled a job. Now we have a valid handle. Then I can schedule another job and pass that handle in as an argument to the schedule call, and that will only allow job 2 to begin once job 1 has completed, and that will happen automatically by the job scheduling code within the Unity player. And then I've got handle 3, so I create another job, and I use handle 2 as a dependency and schedule it. And so the nice thing there is this native array is automatically being transferred from one job to the other. And then obviously the idea is that somewhere in maybe the last job you're able to harvest the results of the work that was done across these jobs. Now where this can be particularly nice is the last job might actually be an iJob parallel 4 transform. So if you were doing a set of computations, maybe you're simulating physics in one job, and then maybe you've got some player code that's like bot type player code, that's like AI basically, that's making decisions about how to react to the physics and how to react to maybe what the human player is doing. Then that could be another job, and then finally you might have a job to position everything and just update the scene, and so that might be an iJob parallel 4. And so with a bit of careful crafting, this can be scheduled by, in the update method, you can set this all up to happen as a pipeline, right, by chaining these jobs. And then only when the last one's complete, right, which is the iJob parallel 4 transform type job, when that one's complete, which you can use the job handle and you can check the isComplete property. When that's complete, it's all done, and then you can actually schedule the next set. So you can actually have a pipeline which you sort of feed at the one end, set them up with the dependencies, let it go. It will automatically update the positions when it's ready, and all of this you don't have to worry about. So it means that this can run in parallel to the rendering of in the main thread, and it makes it simpler to manage this kind of code that might have, particularly if you're dealing with physics and some AI, that might have a bit of complexity to it. So this actually turns out to be really useful. Not only are you then doing work in parallel as much as possible, potentially, you could be using vector math, so you're really starting to make use of all of what's available in the processor. And then you're letting it run as long as it needs to run and complete and make the changes to the transforms. So that actually turns out to be pretty nice. So the other thing that's worth noting with native arrays is you have different allocators. So you can construct a native array, like you just use the constructor to create it. One of the arguments you provide the constructor is the allocator. So you can create a native array to be invalid or none, which is probably a bit curious, but I think because again it's a struct type, so none is probably the default value, or maybe invalid is the not default. But things like temp job and persistent are the ones you're probably going to choose between. I tried temp and found that Unity seems to expect that the native arrays created as temp are destroyed within, as in disposed within a few frames. And if you don't, you'll get an exception about that. The other thing which I actually prefer is the persistent allocator, because I can then create all my memory up front, and I'll just hold on to those native arrays and reuse them through jobs throughout the life of the game. And I like that because it means that the memory footprint of the game is consistent all the way through. And so I'm not sort of always allocating and freeing and then putting pressure on the Unity player to manage and track, what memory is free and available and so forth. I don't know how they manage it, whether they try to use some kind of garbage collector for that, but there's a good chance that could lead to fragmented memory. It's got to have a cost, so I like the idea of allocating my memory up front and having some consistency and simplicity about it. Now, just a couple of little tricks here is when you try to dispose of a native array, you need to make sure that any jobs that were using it are all complete. So I found there's a nice trick, and you can see this in the slide, that in the MonoBehaviour that's managing the native arrays, that allocates them and then later frees them, you can have an on-destroy method. So when that MonoBehaviour is about to run away forever, this will get called by Unity automatically, and then you can use the job handle static methods of schedule batch jobs and complete all to force all of the jobs to actually get executed. Otherwise, you never know, right? If you schedule a job, it may get executed eventually when Unity gets around to it. But if you do the schedule batch jobs, it forces them to all get executed. And then you can do the complete all, which means anything that might still be running, it should actually wait on the complete all. Here you need to provide a reference to all the handles you want to wait on. And then basically, once you've done that, you know that all that memory is unlocked. And once it's unlocked, you can then dispose of that shared array, that shared native array. So for however many of these native arrays you create that you use in jobs, you'll need to basically just make sure that you've completed those tasks, called complete against them, or use the complete all like I've done here, and then you can dispose of them. And if you don't, you'll get an exception. So that is the trick with that. And it took me a little while to figure out that I need to use the schedule batch jobs to force them all to execute. I tried just doing a complete in the on-destroy method, and that didn't work, I think, because complete might require a following frame. It's not clear how Unity make complete work, but this definitely works. Okay, so it's worth noting that apart from multiple threads and that sort of background processing in those threads, the other benefit that you get with the job system is the ability to use things like Unity.Mathematics and the Burst compiler. And the reason why this works together is because they're using value types, and the Unity.Mathematics has been produced in such a way to exploit vector instructions in CPUs. So for instance, the Burst compiler will know how to optimize Unity.Mathematics, and Unity.Mathematics will provide the operations for vector addition, multiply, subtract, and so forth. And the vector values are actually really powerful because, and you also get matrix values as well for that matter. But not only do you get things like int, float, and bool, right? And the bool is actually very cool because it means you can have conditions in the X, Y, and Z, and you can process those in a functional programming type of way. If you've seen my video that I did about using the new input system, this is what I leveraged out of Unity.Mathematics, and that was in the main thread. It wasn't even in the job system, but it's still very, very cool. But the point is that this actually means that you're performing an operation on multiple values with a single instruction, right? So this class of computation is called SIMD, single instruction multiple data. And actually this idea comes from supercomputing back in, I think, the 70s. It was like the Cray supercomputers used to use, they were one of the first to have a vector processing CPU. So anyway, it means that, again, it's another way of accelerating the code you have in Unity. So if we look at the documentation for Unity.Mathematics, Now, the thing is, Unity.Mathematics is a package that you have to install through the package manager. So actually, take a second. Let's have a look at Unity. So in the package manager, if you install mathematics, then you click documentation, then you see this. And this is where you get all kinds of interesting classes and types. So now let's look at the scripting API. Bring that up in a different tab. I love lots of tabs. Okay, so you need to mathematics. So you can see here that we have lots of different types. So bool 2, bool 3, bool 4, but you also have these matrix types. Okay, so and there's lots of variations there. And you have that too with doubles and floats, and in terms of whether you want float 2 or float matrix, or float 3 and so forth. So there's all sorts of different sizes and such, and then half, which is a sort of a half precision floating point. So you've got lots of different options here, but the other cool thing is you can generate random numbers. You can, if we look for it, there should be noise. Where's noise? Noise. Right, so if you want, what's it called? Hang on. See noise. Yeah, okay. So they've got lots of different sort of noise functions. That was the one, Purnell noise, or whatever it's called. Anyway, so the point is, you have lots of different noise functions, so you don't have to even code these yourself. You can actually just leverage these existing noise functions. And as you can see, it'll operate on X, Y values, and which obviously would be the points, and then you'll get probably an intensity value. It depends on each noise function. But anyway, the thing is, this is very cool. So then you have, so there's a math class, and this gives you, okay, so obviously a number of constants, like E, but also pi's in here, and okay, let's get to the methods. This is page is slowing your browser. I don't care. Be patient. Okay, so if we go down here, here we go. We can find things like max, min, sine, cosine. So you have all the regular math functions in here. And that's, in fact, there we go. And that's super useful. So there's lots of things you can do here. Now, the cool thing is you can write code that looks like shader code, but it's written in C#, so it's sort of easier to maintain and debug and so forth. So it's kind of the best of a number of worlds all brought together. And obviously you can deal with quaternions and so forth. So this is very, very cool, and it's definitely worth exploring this in conjunction with your jobs. And the reason for that is, like I said, you get these another level of parallelism with the SIMD, or single instruction, one instruction, multiple data. So here this is literally doing, just as an example, in the slide, you can see that 4 plus 2 and 6 plus 0 and 1 plus 31 and 8 plus 24.8, if you assume that these were float 4s. The addition of these values is all happening kind of independently at each position. And that just speeds things up. And this is supported in ARM and x86 and some various processor types. And the Burst compiler will optimize these and will actually make sure that the native code that's generated is pretty lean. So it's worth using the Burst compiler with your jobs, and it's definitely worth looking at the Unity.Mathematics package and using that.
So if you find this material useful and you think other game development friends of yours might be interested in this, please do share this. Please do like it, as in hit the like button.